Okay, here we go with 9 for pre-calculus, rational exponents and radicals. So some quick review first from what's on Algebra 2, and then we'll start messing around with these. So rational exponents explained. We know rational exponents are radicals, they're roots. So the rational exponents, fractional exponents, we have to remember whenever we talk about rational, that's what we're mentioning. So rational is fractional exponents, and we have to know which part is the root. So remember, what x to the 1 over a, the denominator in the fraction, is the type of root. The index of the root is what that is. So this is the eighth root of x. So most common one is the square root, but there could be any kind of root. So that is the equivalent relationship here of just rewriting it as a radical, so a root. That means when we get a number with or a mixed fraction without a 1 on the top, so b over a, any kind of rational, the denominator is still going to be the root. So this is the a root of x, and then the numerator is the exponent. So numerator, that is the power we're going to use. Denominator, that is the root that we're going to have. Now, the power, the idea is these are both powers. They can be done in either order. So you could say this is the eighth root of x to the b, or you could say this is the eighth root of x, and then all of that to the b power. Both mean the same thing. So let's see about just converting some of these real quickly. Right as radicals without negative exponents. We did negative exponents yesterday. So start out with x to the 1/3. You guys can answer these before I even write them down. So x to the 1/3. 1 over denominator 3. That means it is a cube root of x. 2, we got the 3/4. Think about it real quick. Denominator 4 root. And the numerator 3, so this is x to the 3rd power. Normally, if we have both, if we have a number, we'd like to do the root first if possible, makes the number smaller, then we do the exponent, but really it can be done either way. Number 3, we've got a few different parts here. We do have a negative, remember what that means. We do have a denominator, so 2 on the bottom, so just a 1 on the top. So remember the different pieces that are involved here. So the 2 on the denominator means we have a square root. Square root, you don't have to write the index. You can if you really want to. So there is a square root of x involved. The negative is the reciprocal power. So the negative means we take this whole thing and we put it under 1 to make its reciprocal. 1 over the square root of x. You could make that a fraction of 1 over x, then square root it all. Either way, you could do something like this. 1 over x is x to the negative power. Square root everything if you want to, but you do this separately. It's like a power over a fraction. So we square root the 1, we get a 1, but the square root of x we still write there as x. So think about those as separate pieces. The negative makes it a 1 over, or switches sides of a fraction. The denominator is the radical, the numerator is the power. You guys try number 4, write it as radical without the negative exponents. Try that right now. Okay, as you just saw, the answer for this one is we've got a negative 1 over. We've got a denominator of 2, so square root, and we have a power of 5, so we have x, and I like putting them inside to the 5th power we have there. So that is our correct answer. You don't have to write 1 to the 5th power because it's still 1. You would evaluate any number. All right, let's see. Going on, let's look at simplifying the radical. So simplifying the radical, you've done a lot of this over the years. I know geometry, do Pythagorean theorem, you have to simplify a lot of these. So a little bit bigger number here, so let's remember what we're looking for. 2 basic ways of doing this. Here's what I like to do. We have the factor tree, and we're looking for square roots in this situation. That means we're looking for pairs of factors to use. Remember, the whole idea is that the square root of, let's say, 9 is 3 because Square root of 9 is the square root of 3 times 3, or the square root of 3 squared. We look at its factors, and we find a square root and a squared will cancel each other out. Those are inverses, so we end up with our 3. So we're looking for that idea mixed in to our composite number that we have here of 108. We're looking for squared factors or just pairs of factors as we go. So square root 108, we can start breaking this down. You can start with anything you know that goes into 108. Start with a 2 if you really want to on there. You can start with numbers that you know are perfect squares. So if you know a perfect square that goes into it, go ahead and use that. So for this one, I can think of a couple different things. We know a 2 goes in, it's even. A 4 does go into this. That's a perfect square. That might help you get these. 9 also goes into here. So your choice, what you want to use. There's a lot of numbers that go into 108. So if I look for something like a 4, let's say I chose that one first. 4 goes into 108 27 times, so we split that into 4 27. 4 is 2 and 2, and there's our pair. Okay. Sometimes I know people just look for the perfect square, like a 4, and just circle that one, say that's going to be a 2 when I do its square root, so it's not going to be under a root anymore. I like to look for the pairs. 27, I can do that's 3 times 9, and 9 is 3 times 3. So if I'm looking at these with separate prime factors, I just look at all of them at the bottom and I find them in pairs no matter where they occur on the bottom of my list. So I have a couple of 2s here. We have a couple of 3s. I could choose this pair of 3s if I wanted to. It doesn't matter. There's a pair of 3s there. So my final answer, pairs, outside. Remember, the square root of 2 squared is 2. Square root of 3 squared, to have multiplied, is just a 3. This 3 is not squared anymore. It's all on its own. It stays inside the root. So pairs go outside, leftovers inside. That is 6 root 3. Quick reminder of that. All right, let's try this with something a little bit different. You did a little bit into this, but remember what we looked for in number 6. This was a square root. We looked for pairs. That tells us what we're looking for. Cube root, or it takes 3 of a kind to end up with a perfect cube. We know some perfect cubes. 8 and 27 is a perfect cube. It's hard to find those numbers inside, so I'm just going to do the prime factors and see how many I have 3 of. So something like 40. There's an 8 times a 5. We know that. 8 is, I can just say 2 times 2 times 2. It's okay to split it up farther. No matter how you break up 40, you're going to get 2 times 2 times 2 times 5. There's 3 of a kind. So in my answer, make sure it remains a cube root. If you leave off that cube part of the cube root, that index, you've totally changed what kind of problem it is. So that can't be the right answer. So make sure you keep the index. So the 2, outside, 5, left over, inside. Here we have x to the 4th and y to the 6th with exponents. It's pretty easy because remember, x to the 4th just means we have 1, 2, 3, 4 multiplied together. There's a group of 3, so there's a group of 3 and 1 left over. If you think about it, that's just remainder division. We did 4 divided by 3, and that is 1 and 1 left over, or 1/3. That means there is 1 full x and 1 left inside of a cube root. That's a way to interpret it. So the next one, y to the 6th, we can just say 3. There's 2 groups of 3, so there's y squared on the outside. Or if you want 6 over 3 is 2 with none left over. So there's 2 outside, none left inside the cube root on the inside. So just a quick way with bigger numbers to be able to do that. So here's our final answer. It doesn't look like we have any pieces to combine and multiply together. So we just have 2xy squared cube root of 5x. All right, let's see about just a number. Let's simplify this. So we have an exponent. We know that's a radical. We want to write it as a simplified radical. It's got to have the smallest number possible inside the radical. So there might be a few different ways you could approach this, and I'll come up with the same answer. First thing I'm going to do is rewrite it as a radical. So do it yourself here and see what you get. You can always pause and then continue on. Top, bottom, 4/3. So bottom, cube root, top, fourth power, and we have 24 to the fourth power. Now, this is where, with a number, we want to think about which one we would like to do first. So there are a couple ways we can go through here from here. One way, we can try to simplify the cube root, and then we can do a fourth power. We can do it the other way. Think of a fourth power first, and then do a cube root. But I don't know about you. I don't know the fourth power of 24. So I'm going to combine those two. I'm going to show this a couple different ways. I'm going to think about this just like the variables. Remember, this 24 to the fourth means 24 times 24 times 24 times 24. I don't have to break those down farther. I found a group of 3. So I can say that this is 24 cube roots of 24 to the first one left over. So that gets me well on my way to simplifying. I'm not done. I'm just going to break down the 24 more. So I'm going to think about it and say 24 is, and you can start writing this down, but if you know the numbers as we go, it's 2 times 12. 12 is 2 times 6. 6 is 2 times 3. There we go. 2 times 2 times 2 times 3. There's another group of 2's. So that goes outside with the 24 is 48 cube roots of 3. This step right here, the first one with any exponent, works just like variables. That's the quickest way to start breaking these down. Otherwise, you might be left doing something maybe a little bit like this. Maybe we cube root first and say the cube root of 24 breaks down into 2, 2, 2, 3. So that is 2 cube roots of 3. And now you have to decide that fourth power. It would be around the outside. Everything in there is still to the fourth power. 2 to the fourth power is 16, and you have cube root of, and you want to do 3 to the fourth power, that's 81. And you start breaking that down. 9 times 9, and each 9 is 3. So there's 4 3's. That's a group of 3, and goes out there, and we get 48 cube roots of 3. There's a couple different ways to get it done. Watch for those exponents, and they can do a real quick simplifying. Just by that little remainder division. All right, let's, last one here, rewrite an exponential form with negative exponents, I want to change the radicals into exponential. So basically, here's what these problems mean. It's not what the directions say in the book, but this is what it means. Write this as a product of x and y, okay? We want x to some power times y to some power. And those powers could be negative. They're going to be fractions, so we start with radicals. So you have to figure out what those powers are. How can we split it into that? So the first one, number 9, we saw multiplication x times y. Let's just interpret each one. So the first one, x to the 7th power 5th root. So 7th power 5th root, root on the bottom, power on the top. Times, do the same thing with the y. That's 6th power 4th root, so 6 over 4. Now that's nice, but it's not quite in simplest form. Exponential form is always going to reduce. So x to the 7/5 times y to the 3/2. We can reduce that. So there's our first one. It's a product of x and y, and those are just powers that came out. Number 10, almost the same thing, except we have division. Now one thing on this, we have a 7th root over everything. Remember, this 7th root is a power. And when a power is over a fraction, it gets applied to both. So this really is the 7th root of x cubed over the 7th root of y to the 4th. So you can split apart that radical, 2 parts. So let's see, the x, that's to the 3rd power, 7th root. And let's just think about this y. The only difference is on the bottom. So that's going to be times y. If it's on the bottom, it has a negative exponent. That's what sent it there. 4th power 7th root. There we have our product of x and y, 2 powers that describe that same fraction. All right, that's it with some rational exponents. That goes with a 0, 0, 9 in there, I guess. So go with that. And good luck with that homework. Get me questions to answer. Without the office hours, I will be answering questions with email and everything. So let me know what you have issues with on the homework. Thanks.